Hey everyone, in this video we'll cover question 13 from the 2017 HSC Mathematics Extension 2 exam. So part A, show that r plus s over 2 is greater than or equal to the square root of rs, for r being greater than or equal to 0 and s greater than or equal to 0. Okay, so this is only worth 1 mark, so it shouldn't be too difficult for us. So if we consider the square root of r minus the square root of s all squared, now, since I'm squaring something, that should always be greater than or equal to 0. So we have that inequality there. Now, if we expand that out, it's going to be the first term squared, which is going to be r, minus 2 times the first term times the second term. So that will actually be the square root of r times the square root of s, plus the square root of s squared, which is just s, is greater than or equal to 0. If I bring that term with the square roots to the right-hand side, I'll have r plus s is greater than or equal to 2, and then combining these into one square root is rs, and so therefore r plus s on 2 is greater than or equal to the square root of rs. Okay, and that's the end of that. Now this is actually a specific case of a more general result, which says that the arithmetic mean of two numbers is always greater than or equal to the geometric mean. So let me just write that general case. So general case here says that x1 plus x2 plus all the way up to xn divided by n is going to be greater than or equal to the nth root of the product of those numbers, x1, x2, xn. Okay, so that's just something extra if you've never seen that before. And that's part A. Part B. Let a, b, and c be real numbers. Suppose that p of x, which equals x to the 4 plus ax cubed plus bx squared plus cx plus 1, has roots alpha, 1 on alpha, beta, and 1 on beta, where alpha is greater than 0 and beta is greater than 0. The first part says to prove that a is equal to c. Okay, so we have some polynomial with some coefficients, and we know what the roots of those polynomials are, so actually let's write those down. We have alpha, 1 on alpha, beta, and 1 on beta. These are the roots of our polynomial. And we want to prove that a is equal to c. So a, let's try to get some expression which involves a. So we know that a should be equal to, well, we can get an expression for a that involves the sum of the roots. So the sum of the roots taken one at a time is equal to minus a divided by 1. So just minus a. Alright, so the sum of the roots is alpha plus 1 on alpha plus beta plus 1 on beta. That's equal to minus a. Great, so that's our first equation. We also want to get some expression for c. Now we can see that the expression for c is going to involve the sum of roots taken 3 at a time. So that's the sum of roots taken 3 at a time. That should be equal to minus c divided by 1, which is minus c. Alright, so what are the sum of roots taken 3 at a time? Well, we have 4 roots, and we want to choose 3 of those for each term. So there's should be 4 c3 ways of writing the sum of roots 3 at a time. So that's just something to let you know, to make sure that you've covered all cases here. So we can have alpha times 1 on alpha times beta. We could have alpha times 1 on alpha times 1 on beta. Plus, what else is there? There's alpha times beta times 1 on beta. And there's 1 on alpha times beta times 1 on beta. So that's the sum of roots taken 3 at a time, and that should equal negative c. Let's simplify that a little bit. So in the first term, the alpha divided by alpha leaves just beta. Again, alpha and alpha cancel in the second term, and we're left with 1 on beta. In the third term, we're left with alpha, and in the fourth term, we're left with 1 on alpha. So that should be equal to negative c. And so that's equation 2. So clearly we can see that in equation 1 and equation 2, the left-hand sides are equal. it's actually equal to the sum of roots taken one at a time. So therefore, 1 and 2 tell us that negative a equals negative c, that is that a equals c. And that's the first part. The second part, using the inequality in part A, show that b is greater than or equal to 6. Okay, so let's actually move this down because we want to see what the polynomial is. So we want some expression in terms of b. So somehow we need to involve b in this in our working. So again, we can use our sum of roots and product of roots business. So here we're going to actually be looking at the sum of roots taken 2 at a time, and that's going to be equal to positive b divided by 1. So I'll just write divided by 1, but that's equal to b. Okay, so what are the product of roots taken 2 at a time? So, like I said before, when we had 4 choose 3 possibilities, here we're going to have 4 choose 2 possibilities, which is 6. So that means that on my left-hand side, I should actually have 6 terms that I'm adding up. So we have alpha times 1 on alpha, plus alpha times beta, plus alpha times 1 on beta, plus 1 on alpha times beta, plus 1 on alpha times 1 on beta, plus beta times 1 on beta. And that's equal to b. Okay? So we can do a little bit of simplifying here. First term and the last term are both going to be equal to 1 because their alpha and alpha will cancel and the beta and beta will cancel. So that's 1 plus 1, which is 2. Here I have alpha beta in the second term, and in the second last term I have 1 on alpha beta. So let's group those two together. Alpha beta plus 1 on alpha beta. So that's that term there and that term there. And then the two middle terms are going to be alpha divided by beta plus beta divided by alpha equal to b. Okay, now the question said using the inequality in part A, I need to show that b is greater than or equal to 6. So, to use the inequality in part A, let's just rewrite what that was. So I'll write it on the side here. That was r plus s divided by 2 is greater than or equal to the square root of rs. Alright, now we can actually rearrange that, and we'll get r plus s is greater than or equal to 2 times the square root of rs. And the reason I've done that is because written in this second form, we can say that the left-hand side is just two sums, is the sum of two terms. And I can actually see that here and here I have the sum of two terms. And they just so happen to be grouped together because I can see that they are actually reciprocals of each other. So I can actually apply this inequality to these two individual terms. I can say that this one here should be greater than or equal to 2 times the square root of alpha beta times 1 on alpha beta. And this here should be greater than or equal to 2 times the square root of alpha on beta times beta on alpha. And you can see in both cases, that square root, we're actually square rooting 1 because alpha beta divided by alpha beta is 1. So this is actually equal to 2. So these two terms which are grouped in brackets, both of them are actually greater than or equal to 2. So what do I have? Let's move this up a little. I have b, that's going to be greater than or equal to 2 plus 2 plus 2. And so therefore b is greater than or equal to 6, and that's the end of that question. Part C. A particle is projected upwards from ground level with initial velocity a half root g on k meters per second, where g is the acceleration due to gravity and k is a positive constant. The particle moves through the air with speed v meters per second and experiences a resistive force. The acceleration of the particle is given by x double dot equals minus g minus kv squared, meters per second squared. Do not prove this. The particle reaches a maximum height h before returning to the ground. Okay, so now the actual part of the question, using x double dot equal to v dv on dx, or otherwise show that h equals 1 on 2k log of 5 on 4 meters. Alright, so that's quite a lot of information, but there is really only 2 or 3 things that we need from that. So obviously we need this differential equation here. This is known as a differential equation. X double dot equals minus g minus kv squared. What else do we need? We need that the initial velocity, so that means when t equals 0, we have x equal to, well, we can take the ground as our origin, so x equal to 0, and we have v is equal to 1/2 the square root of g on k. What else do we have? We have that at the maximum height, we have a maximum height of h. So that means that x max equals capital H. But what else happens at a maximum height? Well, at the maximum height, the particle is just about to start coming down. So it's not going up anymore. That's because its velocity has reached 0. So the velocity is equal to 0. Okay, so these are our 2 main bits of information that we need to extract from that long paragraph that I just wrote out. And what else? We're told that using x double dot equal to v dv on dx. So they've pretty much told us that we need to substitute v dv on dx for x double dot. So let's go ahead and do that. Now let's get all the v's together and all the x's together. Okay, so what I'm going to do, I'm going to factor out a -1 on the right hand side and then divide by g plus kv squared. So I'm going to have v dv divided by g plus kv squared. That's going to be equal to negative dx. Okay, and I'm going to integrate both sides, and I'm going to have some limits for my integration. So when x is equal to 0, my velocity is the initial velocity, which is 1/2 root g on k. And when x is equal to h, that is at the maximum height, my velocity is equal to 0. Okay, so you can see that these limits need to match up. Now we can go ahead and try to integrate that. So the right hand side is actually just going to be negative x, so I'm going to write that here, negative x, and that's going between 0 and h. Now for the right hand side, I have a v squared term in the denominator, and I have a v in the numerator. So this is almost going to be a log. What I need to multiply by 2k and divide by 2k. So if I do that, I will be able to straight out use a log. So that's going to be 1 on 2k times log of the denominator, which is g plus kv squared. And our limits are 0, 1/2 root g on k. Alright, let's move this up now. Alright, so the left-hand side is going to be negative h. The right-hand side, let's go ahead and substitute in our values. So the first one is going to be log of g plus 0, so just g. Now, since this is going to be a log minus a log, I'm just going to combine those 2 logs into 1, and that becomes a division. So for the 1/2 root g on k, if I sub that in, that gives g plus k times 1/2 root g on k all squared. So hopefully that's not too small or too messy. That's a k there. Okay, that probably made it a bit messy, but never mind. So that's 1 on 2k times log of, right, let's try to, oh, what have I done here? Why is this log? That shouldn't be a log there. That should just be the, actually let's just rub it out and rewrite it. Alright, so that is, let's see, that's g plus k times 1/2 the square root of g on k squared. Alright, that's better. And then we have g on top, and here I have g plus k times 1/4 times g on k. Okay, so k cancels with k, and I'm left with 1 on 2k log of g on g plus 1/4 g, which is 5 on 4g. 5 on 4g. This g cancels with that g. So I have 1 on 2k log of 4 on 5, but that's equal to minus h. So if I multiply by negative 1, I get h equal to negative 1 on 2k. But I'm going to use that negative and bring it as the power of my log. So I have 1 on 2k log of 5 on 4, which is what I want to prove. Part D. The trapezium whose vertices are A, 0, negative 1, B, 0, 1, C, 4, 3, and D, 4, negative 3, forms the base of a solid. Each cross-section perpendicular to the x-axis is an isosceles triangle. The height of the isosceles triangle ABE with base AB is 1. The height of the isosceles triangle DCF with base DC is 2. The cross-section through the point x, 0 is the isosceles triangle PQR, where R lies on the line EF, as shown in the diagram. Find the volume of the solid. Okay, so here we're finding volume by using the slicing method. So we want to find the volume of one slice, PRQ. So that's one arbitrary slice, PRQ. All right, so first let's label a few points. Let's call this point here point G. Let's call this point here point S, and this point here point H. So hopefully you can see all those in the video. All right, now we want to find one slice, the volume of one slice. Actually, let's use black, keep it consistent. Delta V. Now that's going to be the area of triangle PRQ times delta X, because that's the thickness of the volume. So we will see that if this was a slice, it would have a thickness of delta X on the x-axis. So maybe I can indicate a thickness like that. Okay. So now the problem is we need to find the area of triangle PRQ. All right, so the area of triangle PRQ is going to be half the base times the height. So it's going to be a half. The base is PQ, and the height is RS. But the base is cut by this altitude. It's not cut, it's bisected, so it's cut in half. So that means that a half of PQ is actually equal to SQ. So I can write this as SQ times RS. So now what I need to do is I need to find expressions for SQ and RS in terms of X, so that I have an expression for the area, and then I have an expression for the volume in terms of X. All right, so let's go ahead and do that. So to do that, we're going to need to consider some similar triangles. So firstly, we're going to be looking at, now I'm going to go over it in green, we're going to look at this shape here. Let's have a look at this one. Okay, so let me draw that. Let's slide this up a little. Let me draw that now. So that is going to be something like this. Have this trapezium looking shape. Now we know that this point here is point H. This is point E. Let's go back. This is point C. And this is point G. Now we also know that this length here is 1 unit. So if I draw a line parallel to HG, that means that this line, or this distance here, is also 1 unit. And I want to involve S and Q and P. So I'm going to draw this line here, which is really representing this bit here, SQ. All right, so this is the point S here, and this is the point Q here. Okay, so we know that the distance HS, because S is at x, 0, and H is at the origin, so therefore the distance HS is x. Okay, so we have that, and we know that this distance here, CB, from the diagram, this is equal to 3 units, which means that this distance in here should be 3 minus 1, which is 2. So we can use similar triangles in this diagram here. So that would be the smaller triangle and the larger triangle are similar. We don't really have to prove that because it's actually quite obvious, and at our level of Extension 2 maths, they would assume that we know how to do that. So anyway, you could prove it if you wanted to, but there's no point. We have similar triangles, and we know that the ratio of the side lengths, or the side lengths are in the same ratio of similar triangles. So therefore, we have the length SQ minus 1. So now I'm referring to this length. That's SQ minus 1. Divided by 2, which refers to this length here. That should be equal to x, which is this length, divided by 4, which is the whole length of HG, which I forgot to put in my diagram. So this whole length here is 4. Okay, and so I can rearrange that, and I can get SQ equals x on 2 plus 1. Now I can do a similar thing with a different diagram, but again we'll be using similar triangles. So I have the same shape, but this time, let's indicate it on our original diagram, we're looking at this in blue. So all the way up, so now we're going up, down on this altitude of that side. So we're looking at that blue one, so hopefully it hasn't gotten too messy. Okay, so this is point F, this is point R, this is E, this is H. Again, this is a length 1. This is the point G. Again, this length in here is X. Let's slide it up now. What else do we have? We have that, well, let's just see, this height here is 2. So that means this height in here is 1, because this is also 1. And I think that should be enough. Oh, of course, don't forget this length here is 4, as before. And so yes, now that should be enough. I should label that as S. That should be enough to tell us, or for us to find RS. Again, by similar triangles, RS minus 1, so this is referring to this distance here, RS minus 1, divided by 1, and that 1 is referring to this bit here, should be equal to x divided by 4, in the same way as before. So here is our distance x, and 4 is, of course, the whole length hg. And so I can rearrange that, and I get RS equal to x on 4 plus 1. Okay, let's continue. So therefore I have that the area of PRQ is SQ times RS, which means it's equal to x on 2 plus 1 times x on 4 plus 1. Now that should be x squared on 8 plus 3 on 4x plus 1. And so therefore, delta V equals that expression, x squared on 8 plus 3 on 4x plus 1 times delta x. So we have the integral of, or the entire volume, let's fix that up, the entire volume is equal to the integral from 0 to 4. Now why is it 0 to 4? Because I'm going from 0, which is at h, x equal to 0, to x equal to 4, which is at g. So from 0 to 4 of delta v, which is x squared on 8 plus 3 on 4x plus 1 dx. Integrating gives x cubed on 24 plus 3 on 2x squared, sorry, 3 on 8, that should be an 8, 3 on 8x squared plus x between 0 and 4. Subbing 4 in, I'll have 64 on 24, which is going to be 8 on 3. Here I'll have 3 times 16 divided by 8, so 3 times 2, which is 6, and here I'll have 4. And when I sub in 0, I'll be left with just 0, so that'll be minus 0. And so this adds up to 10 plus 8 on 3, which is 38 on 3 units cubed. And that is our volume. Part E. The points A, B, C, and D on the Argand diagram represent the complex numbers A, B, C, and D respectively. The points form a square as shown on the diagram. By using vectors or otherwise, show that C equals 1 plus I times D minus I times A. Alright, so in this question, we can see that what we need to prove is that C equals 1 plus I times D minus I times A. So actually, what we need to prove doesn't include B at all. So let's just keep that in mind. Now, back to the question. We have some diagram here and we have a square. And what do we know about squares? Well, firstly, we know all side lengths are equal, but we also know that every angle is a right angle. So that means the vector DC should be equal to a 90-degree rotation anti-clockwise. Sorry, DA is a 90-degree anti-clockwise rotation of DC because they have the same length, and the only thing that's different is that they're at 90 degrees. So if I rotate it by 90 degrees, then I get from DC to DA. But that also applies to vector BC and BA, and to vectors CB and CD. So how do I know which one I need to use? Well, we go back to what I just said earlier, where we look at what we're required to prove, and we see that we don't want to include B. So we want two vectors which are at 90 degrees and don't include B. So that's going to be DC and DA. So I can say the vector DA is DC rotated anti-clockwise by 90 degrees. So if it's being rotated anti-clockwise by 90 degrees, that means we have the following. DA is going to be equal to DC times I. Right, multiplying by I is the same as rotating anti-clockwise by 90 degrees. So, what is DA? Well, DA is the vector that starts at D and goes to A. So that's going to be equal to A minus D. And DC is the vector that starts at D and goes to C. So that's going to be equal to C minus D times I. Alright, so this is CI minus DI. So therefore, I have, now we want to get C equal to, so let's keep C on one side and move everything else to the other side. So we have CI equal to A plus, and I can factor out a D, and I'm left with negative 1 plus I. Alright, but I want to have C by itself, so I'm going to multiply through by negative I. The reason I do that is because when I multiply on the left-hand side by negative I get negative I squared, which is positive 1, so it leaves just C. So multiplying everything by negative 1 gives me C equals, sorry, by negative I, gives C equal to negative AI minus ID into negative 1 plus I. Distributing the negative I through this bracket gives me negative I times negative 1 is positive I. Negative I times I is negative I squared, which is positive 1. So therefore I have 1 plus I times D minus AI, which is what I wanted to prove.